So earlier in the first session, we discussed that regardless of the external E field, there will be a polarized field. Of the matter will be polarized along this E field, and then the the dipole moment per unit volume is represented by this capital P. So this capital P is due to this E field but it will also generate a new field, and this new field is something that we are interested in. So we want to study what kind of field this polarization vector will generate. So now we can, the first step is that we can simply use the superposition principle. Now, for this entire object, we simply say that for infinitesimal volume, it's the d tau prime. And if we are interested in the V scalar potential somewhere at R, we can simply do a superposition principle and you do a integration over the volume of this object, and this will give us this scalar potential at an arbitrary observation point at R. Now we can do a trick by using integration by parts. So remember that here this is the del operator that's with respect to R prime, because there is a prime vector here, and this separation vector is dependent on both R and R prime. So there is this now we can move this term out of this integral by this integration by parts. So there for any integration by parts, there are always two terms. So the first term is by moving this operation to the left. So that is the term over here, and the second term is by combining these two terms and move this integral to the outside. So so this first term can be is a combination of the two terms here, and this term we can apply the divergence theorem and reduce this volume integral to a surface integral, and the second term is kept the same. Now let's take a closer look at this first term. So you can actually see that this is actually exactly identical to the potential for a surface charge, where the surface charge is p dot n, and then this means that this term is actually saying that what this p vector gives, at least one term, is equivalent to an induced charge on the surface of your object. So remember that we are always looking at this finite size object, and on the surface of this object there will be some induced charge, and it's defined by p dot n. And now there are also the second term, and the second term, if we look closely by comparing with the potential for an ordinary charge, so if we replace this by a rho, then this simply gives us the expression of scalar field for an arbitrary charge distribution. So this del prime dot p can be identified as another charge, which is a volume charge of distribution. So this suggests that not only there might be induced surface charge on the edge of this object, there might also be additional volume charge distribution throughout the space of this object. So now if we combine them, this means that the potential generated by this polarized material can be separated into two terms. One is the induced surface charge term, and another is induced volume charge term. Now let's try to go through an example. So So here, this example is asking to find the E field produced by a uniformly polarized sphere of radius r. So when I mean uniformly polarized, you have to be careful about the wording here. So what 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 do you think would mean by a uniformly polarized object or a sphere? Uh, the charge might not be uniform, right? At least you have to change the charge to dipole. So the yeah, the dipole distribution is uniform, and what I mean here is that the when I say uniform here, this p is independent of the coordinate within this object. So p is independent of x, y, z, right? But p itself has a direction, and so this means that the direction must be fixed. You have to choose a direction by yourself, right? So and if you align the z-axis along with the direction of the p, then this is what I draw here.
So you're saying as long as the direction doesn't change, even the magnitude may depend on the coordinates, doesn't it?
The magnitude also does not change. The magnitude of the p also.
The
Yeah, the magnitude and direction of the p is the same throughout the space of the object only. So if you go out of the object, then apparently that's zero. Now, if you calculate the field generated by this sphere, I think so you have to first calculate the charge distribution, right? So we go through the charge distribution earlier. So there will be a surface charge distribution. Sigma bound, which is p dot n hat. I guess that should be correct. So then this is simply now if we define the center of the origin, if we write this in spherical coordinate, that will give the p cosine theta, and the bound charge here should be used as rho. Minus del dot p. So this term is exactly zero because p is a constant within the object. So now you see that this is actually can be considered as an alternative problem where there are only surface charge distributions throughout the surface of this sphere, and this problem is already solved in our previous lecture. So if you look up your notes in the lecture, and this is the result for the potential. And now you can calculate the E field of this potential. And if we calculate the E field within this sphere, it's actually turned out to be directly proportional to this polarization vector P. So this means that within this sphere, the E field is actually a constant. And now we can also take a look at the potential outside of this sphere, and this potential is actually the same as the perfect dipole potential. So the answer of this problem is actually extremely simple. So inside this sphere, it's a uniform and constant E field, and say it's actually pointing downwards, and outside this sphere, there is a very nice dipole distribution, and this is simply a combination of the two solutions. So the problem can also be solved in an alternative way. So instead of looking for the bound charge distributions by doing the P dot n and the del dot p, we can also think of intuitively as a uniformly polarized sphere by aligning two spheres of opposite charge. So here the top sphere is of uniform plus charge, and the bottom sphere is of the uniform minus charge. And I don't know if you still remember, but we actually calculated this problem in the previous homework 1, I guess. And if you can look up your notes, you might discover that you actually found something similar to this dipole outside, and you also should be finding out that inside the E field is independent of the position, and it's a constant. So now in this picture, you can readily see that the dependence on this the bound charge surface charge angular dependence is cosine theta, because you can kind of imagine that the volume on this top here is decreasing as you go through this the angle goes maybe I should go through the other way. So as this theta goes from 0 to pi, this charge, the total charge area where there are positive charge is reducing, and it's dependent on the cosine theta. Okay, so this. So what I'm right now, what I will discuss is some advanced topic. So if you don't understand what I'm saying, you can try to look through the Griffiths more times, or try to find out the discussion. I think it's at the first section between the I'll give you the page number later. Um, here, what I'm trying to argue is that in what we study is the classical E and M. So we don't care about the microscopic nature of a material. So in principle, if you polarize a material, the positive charge and negative charge might separate. And if you consider an electron, and if you go very close to an electron, the induced field will be huge. And but what we say before is that the E field are supposed to be constant, and so that's very different from the microscopic picture, right? So our argument is that we are studying a classical picture, and we always look for the average instead of instantaneous uh, a very microscopic distribution of electrons within the space, and then can look for the exact moment of an electron and calculate the exact E field. And but what we our calculation can be think of an average over a slightly larger space. So our interest regime will be including thousands of electrons, say. And this effect, if we average over this a large volume, so then the electric field over this volume will be constant. So instead of looking for the very details of electric field very close to an electron, and this actually can be nicely proved by the homework that you have done in homework 2, question 4. So now what I mean is that here, instead of calculating the E field, we want to we want to replace the E field by an average over a volume of the E field. And then this field has two contributions. One contribution is the E field that is outside the area of interest. Say this is the integration area, and we want first the field to be we first calculate the E field that's far away from this area of interest. And then this E field is simple. We can use the dipole approximations, and everything should be working perfectly. And then we need to calculate the inside of this electric field. The inside of the E field can be a bit complicated because the dipole approximation no longer works. And so for the first step, if we look at the if we look at the fields outside produced by the outside of this dipoles, so this is simply the integrating over all the contributions by this dipole, and so this is exactly the same as what we discussed in the very early. This is simply the superposition of this dipole, and think we also okay, and now this is only one part of this potential. The other part is so this one is being proved in the homework question D, and what's left over is the E field due to the charge distribution inside of this sphere. And this problem has been worked out in homework 2, question 4, A through C. And we actually find a very compact solution for that, that for an arbitrary charge distribution, no matter how complicated that is, the inside electric field must be proportional to the dipole, the total dipole moment, and divide by this r cubed, and that includes every possible electron distribution that you can think of. Now, if we rewrite these terms in terms of this p vector, so that is the average over the sphere, you can actually get back this 1/3 epsilon naught p. This is actually exactly what we derived earlier for this uniform polarized sphere of radius r, right? So this means that we actually put back the E field that we taken out earlier, and now if we sum the fields outside and sum the field inside, then the total field will exactly follow the potential formula of this one, except that the integration is not only done outside but also inside. So this is what I mean by microscopic picture, and the field really we are interested in are the average over a certain volume, and this volume cannot be too small. Okay, so let's take a few more examples. So the example that I want to give is the say there is we are interested in a capacitor, and so we previously calculated the capacity of a parallel plate capacitor that is in vacuum, and so for the vacuum the uh, so the vacuum, the dielectric constant is too small, so the capacity is actually small. So oftentimes for capacitors, we have to fill in materials, fill in dielectric materials to enhance the energy stored in capacitors. So so for example, that we are trying to get some polarized materials that if say for this the slab of thickness d, and all these materials are infinitely are constantly polarized, and now if we look at the surface charge of this material, there are two possible charges. One is the bound charge, and that is one is the bound charge on the surface, and that is on the top and the bottom surface. So here this P should be dotted as the here we choose the direction of the P to be along the z-axis, and now you can see that there are no charges on the sides, and only the top and the bottom surface has the surface charge, and this surface charge is P for this upper surface, and it should be a minus p for this lower surface. And again, because this is a constant polarized material, so this bound charge in the volume is del dot p, and because p is a constant, so this is 0. So this means that now what this material does is it will induce two surface charge. One is at sigma equals plus p, another is at sigma equals minus p, and they are separated by this distance d. Now, if you want to calculate the electric field generated by this material, then you can use the Gauss theorem and add a small pillow box, say on top near this surface, and you can calculate the E field. So the E field generated by the top generated by the top surface charge will be perpendicular to the surface, and it will be E point on the upper surface and also E on the lower surface. So there is E times twice of the area, and which is equal to the surface charge, and now this E field produced by this upper surface is the and it's along this direction of the direction of the E should be outside. It should be up at along the Z, and inside it should be along the minus Z. And now if you calculate the same thing for the E field along this bottom surface charge, it's exactly the same calculation, but the field is going to be pointing inwards. And now if you combine the field of the two, you actually see that in the plane that's above this material, the 2E field will exactly cancels out, and also for the 2E fields also below the bottom plane, the E field also cancels out, and the E field within the plane should be twice of this E, so it will be, and because it's pointing downwards, and so there is a minus sign here. So for this kind of material, there will be only electric field within this slab, and this is quite different from this uniformly charged, uniformly polarized sphere, where there might be dipole fields leaking outside. So that's also why this is good. That's why this is an ideal construction of a capacitor, because capacitors are trying to confine the electric energy inside of the capacitor, and in this way it stores entire of this energy inside of this material. Now, the physical explanation of this phenomena that we see can be explained like this. So we see that the E field actually induces many tiny dipoles. So if you think of them as dipoles like this, if they form a chain, and in the inside, the positive charge and the negative charge actually exactly cancels out. So for uniformly charged materials, the because this del dot p is 0, so in the end they accumulate, and what's left over is there are certain surface charge on the two ends, and now I also want to say that this even though there is a clear distinction of this the volume charge and the surface charge. Um, they are actually uh, the same in the sense that so if you consider this derivative of the p along this edge, say that you try to apply this surface volume charge to the edge of this surface, and now you actually see that this and for simplicity we focus along this z line, and now you can actually see that the p function is a step function, and then the derivative of a step function is actually a delta function, and because here this p is pointing the inverse step function, so there is also a minus sign, and now this delta function actually corresponds to a surface charge, because the charge you can see that will accumulate on exactly the edge of this delta function, and actually you can also relate a surface charge to a volume charge by a delta function. So in principle, these two are the same thing, and you can represent your induced charge by rho bound only. Now let's take another example of uniformly charged material. So so this time we will look at cylinder. So even though I only draw a circle, and it's similar, you might think this is the same old problem of sphere, but it's actually a slight variation, and it's actually a cylinder, and I didn't draw the other z-axis. So there should be a z-axis, and now I want to look at what happens to this uniformly polarized cylinder. And the trick that I want to use here is actually the one that I mentioned. So exactly calculating this surface charge might be difficult if you don't know the cylindrical functions to expand your B potentials. So here, alternatively, we can think of using the same picture of what we mentioned before of a two uniformly charged sphere, and simply we replace them by a two uniformly charged cylinder, but they are spaced by a small distance d. So this d should be infinitesimally small, and in that case, we will recover our uniformly charged cylinder. And in this case, you can use the Gauss law to calculate the E field, and so there will be an E field generated by this plus cylinder, and an E field generated by the minus cylinder. And so for an E field generated by the plus cylinder, we can use the Gauss law. We can simply use use a Gaussian surface that is also a cylinder, but is smaller in radius, and so that will determine the E field inside, and so for the inside of so for the E field inside of the cylinder, if you use the cylinder, you can actually determine that the E should be here. I use S to represent the radius, and so this is the symbol that the Griffiths chose to use. So sometimes we also use R or rho, but they try to differentiate from the cylindrical coordinate to the spherical coordinate, and the rho is sometimes also reserved for this charge density. So that's why the S is used. So this is simply from the Gaussian formula. And now for the E field, for the minus charge, this is also similar, except that the charge is of negative, and the S is also slightly offset. So one is at the center of the plus charge, and the one is at the center of the negative charge. And now we also know that this one S plus and minus S minus is the separation vector between the two center, and so this means the total E field with the addition of the E plus and the E minus can actually be written as the proportional to the d vector. So this is actually very similar to the conclusion that we have for the two spheres, and except that this is for a cylinder. And now, because this P defined as Q times D, and then this is, remember that this is the small p, which is the total dipole moment, and then you can think that the capital P, which is the total dipole moment per volume, should then be written as the rho times the separation vector, and this means that the E inside should actually really be the capital P divided by 2 epsilon naught. So this is slightly different from the case of this sphere. Now this is the field inside, and for the outside field we can also use the Gauss law. So this time we are choosing a slightly larger cylinder for the area of integration. So so here on the left hand side is still the same, but for the right hand side, remember that we have a cutoff, and it's bounded by the side of the cylinder. And now bear this difference in mind, we see that for this the E field introduced by this plus charge will be the form over here. And now if we add this E field together for both the plus and the minus charge, I'll skip the details. So here the S plus minus is this S vector. So if you simply finish this calculation, you will guess that. Let me see. So here, what I'm trying to do is to expand the Taylor expands the d over s, where considering the s is much larger than the d, and now you can actually so this is valid because here our two dipole moment. Remember that we even though we are separating off these two cylinders, what's really in the end that we need to take this d goes to zero limit. So even though this is an expansion, in the end, after the limit, this if we will get some exact results. And now if we put that and combine the two terms, we will arrive at, in the end, and finally we simply now we calculate the terms over here. So now we plug this in inside, and the final expression for this E field should be and here this capital P is simply the rho times D. And this gives us both the E field inside the sphere, which is inside the cylinder, which is a constant, and outside this cylinder, which is something complicated. But the combined effect will be, if I draw this here, it will be a constant field inside, and outside is something like this is actually a very special thing. And if you look at the magnetic field, so this is actually the expression is actually the same as the magnetic field. So this is actually the electric analogy of a magnet, and it's called the electronet, something like this. I don't remember exactly the terminology, but this kind of material where the uniformly charged inside is actually rare in nature, and there are only a few materials that have this kind of permanent uniform polarizability, and unlike the magnets where you can find them everywhere.